Okay, folks, I want to do a quick proof of what's called the product rule. And our goal is to show that if we take the derivative of a product of two functions, notice that I've got f of x, it's being multiplied to g of x. How do I take the derivative of the product of those two functions? Unfortunately, when you take derivatives of products, it doesn't work out as nicely as when we took derivatives of the sums. That means that you can't just distribute the derivative operation over the product. Okay? Instead, when we take the derivative of the product, it'll be the first function times the derivative of the second plus the second function times the derivative of the first. I like to sometimes annotate this as the first d second plus the second d first. So I'd like to prove that this rule holds, and so we're going to have to fall back upon the limit definition of the derivative. So suppose f prime of x and g prime of x exist. Okay. So let's now look at the limit as h approaches 0 of their product, which would be f of x plus h times g of x plus h minus f of x times g of x all over h. So what am I doing? I'm using the limit definition of the derivative, but I'm tailoring it here for the product function. So this is equal to the limit as h approaches 0 of f of x, f of x plus h times g of x plus h. And here's our little trick here for this particular limit. I'm going to first subtract the factor f of x plus h g of x. It's not entirely clear why I'm picking this factor, but I'm going to write it first as subtraction, then as addition. So one way to look at this is I'm adding a net of 0 inside this expression. Minus then f of x times g of x, and this will all be over h. Okay, so one more time, what was that step? Well, I took an expression here and subtracted it inside the larger limit, and then I've added it back to it. So the net of these two is 0, so I haven't changed anything. But now this allows me to group things in sort of a different way. So I'm going to now rewrite this as the limit as h approaches 0 of f of x plus h g of x plus h minus this first term, f of x plus h g of x, all over h, plus the limit as h approaches 0 of f of x plus h g of x minus f of x g of x. And I'm about out of room here. Let's see what we can do. Well, I don't need the color anymore, so we'll try that. F of x, g of x, all over h. So folks, essentially what I've done is if we had the fraction a plus b over c, I've broken it up to be a over b plus, well, that's not quite right, a over c plus b over c. Okay, so I took, yes, I'm going to work with the colors. I took these two terms here, and there's that fraction, and then these two terms here over h, that made that fraction. Now I'm using the limit sum property, but eventually I need to show that both of these limits exist. That is, I broke the limit over the sum here, and that's permissed as long as each of these limits ends up existing, and we will see that they do. So let's continue. So notice that in this inside this first limit, both terms in the numerator have a factor of f of x plus h. So I can go ahead and factor that out of the numerator. Plus, and then notice in this fraction, I've got two factors of g of x. I can first factor them out of the numerator just like I did before, so I will, but eventually we'll see that they can come entirely out of the limit. Okay, and if you like, you could think of those as over 1 if that helps you think about what we just did. So we factored it out. Now, I'd now like to distribute this limit over the product here. So this is f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x all over h plus, now here notice that for this first factor, the variable in here is x. Well, that is not what our limit variable is. So g of x, although it's a function, is constant as far as h is concerned. And what do we know about constants? We know we can factor them out of limits. So I'm left with this. Okay, great. Now, this limit right here is just f of x plus 0. Why is that? Well, it's actually kind of a subtle argument here. What allows me to evaluate this limit through direct substitution? Well, normally what do we require to be able to evaluate a limit through direct substitution? We require that it be continuous. Do we know that f is continuous? Well, I didn't come out right and say that f is continuous, but I did say that f is differentiable, which means that for any values for which it's differentiable, it's also continuous. So by saying that the derivative of f exists, I said that it was continuous, and so that's what allows me to evaluate that with direct substitution. Now, this part takes a clever eye, I think, sometimes. What is this expression right here? Well, this is just simply the limit expression for the derivative of g, and we've already said that g prime of x exists, so we just replace that with g prime plus g of x, and then for this expression right here, this is the limit definition of the derivative for f of x. So finally we end up with, after I evaluate that, well, that would just be f of x times g prime of x plus g of x times f prime of x. And there you have it.